Friends, welcome to this lecture series. Today we are going to see nuclear physics, and in that we are going to discuss the topic of radioactivity, to which you might have been introduced in class 12th. So what is radioactivity? Consider this simple figure which is shown in this slide. It is an atom of an heavy element. Heavy element are those whose mass number or atomic number is very large, and a heavy element is characterized by a nucleus having large number of protons and neutrons, which is shown here at the center, and electrons are revolving around this nucleus in their orbits, which is shown by these elliptical orbits. Now here we can see three different Greek letters: alpha, beta and gamma. Alpha represents the alpha radiations which are emitted from that atom. Beta and gamma also represents the beta and gamma radiations which are emitted from that nuclei of an heavy element. So how can we define radioactivity? The spontaneous emission of radiation, which can be alpha rays, beta rays or gamma rays, by a heavy nuclei in order to attain stability, is called radioactivity. So in this slide, the central part in blue and red, it represents the nucleus of an heavy element, and from there alpha radiations can be emitted, or beta radiations can be emitted, or gamma radiations can be emitted. Now why do a nuclei of heavy element emits this kind of radiation? Or in short, why is there a phenomena of radioactivity in a nuclei of heavy element? So we are going to see why is there emission of radiation. The basic answer to this is the radiations are emitted mainly to acquire stability. Now how is this happening in this particular nuclei of an heavy element? I have mentioned it previously that a nuclei of heavy element consists of large number of protons and neutrons packed together in a very small space. Now, if the nucleus is such that the number of protons is very large as compared to the number of neutrons, means protons are positively charged, means the nucleus is having more positive charges. In that case, the nucleus becomes unstable. It tries to attain stability by reducing its positive charges. So what will it do? Two protons and two neutrons which form an alpha particle. Now remember that alpha particle is nothing but an ionized helium atom. So two protons and two neutrons, they form an alpha particle and they are emitted out of the nucleus in the form of alpha radiations. So what will happen? After some time, the total positive charge will go down. It will decrease, and hence the nucleus may become stable. It may attain stability. On the other hand, if the number of neutrons is very large as compared to the protons, now in this case the nucleus is again unstable. It will try to attain stability by emission of beta particles. Now beta particles are nothing but electrons. It can be an electron, E negative charge, or it can be a positron E positive charge. Now, where are these electrons and positrons coming from? They are coming from the breakup of the neutrons. The neutrons breaks into a proton and a electron, positive and negative charges, and these electrons are then emitted out of the nucleus in the form of beta radiations. So we have seen about alpha radiations and beta radiations. But what about the gamma radiations? Now I have mentioned that a heavy nuclei consists of large number of protons and neutrons, and the nuclei initially itself may be in a highly energetic state. It may be in an highly energetic state, then it is unstable. In that case, in order to attain stability, the atom in that particular element or a substance, it may make a transition from higher energy to a lower energy. And whenever there is a transition from higher energy to lower energy by the atom or by the nucleus, then in that case the difference in energy between these two levels, higher level and lower level, this difference in energy is given out in the form of energy, and this energy is mainly electromagnetic in nature, and hence sometimes photons are emitted, or sometimes gamma radiations are emitted. So we have seen that the basic reason why the radiations, alpha radiation, beta radiation, or gamma radiation, is emitted from the nucleus of an heavy element. It is mainly because it wants to acquire stability at any cost. So the radiations are emitted to acquire the stability. Next, we see the law of radioactive decay. The simple statement for this law of radioactive decay is that the rate of radioactive decay, which is denoted by minus dN upon dt, that is radioactive decay per unit time for an element, it depends upon the total number of nuclei, capital N, present at that instant of time. So rate of radioactive decay, it is directly proportional to the total number of nuclei of the element present at that instant of time. The rate of radioactive decay is independent of external physical conditions like temperature, pressure, chemical composition, or form of that particular element. Now, if I want to represent it mathematically, I can write the rate of radioactive decay, that is minus dN upon dt, is directly proportional to capital N, that is the total number of nuclei of that particular element at that instant of time t. So here minus dN upon dt, it represents the rate of radioactive disintegration or radioactive decay. Capital N, it represents total number of nuclei present at that given instant of time t. And what does the negative sign here indicates? It indicates that N decreases with the time. It is quite obvious. If disintegration takes place, if one disintegration takes place, we lose one atom or one nuclei. So N goes on decreasing as time increases. That is represented by the negative sign. Now let N0 be the total number of radioactive nuclei at the time t0. Let capital N be the number of radioactive nuclei at any instant of time t. Now from equation 1, we have seen that rate of radioactive disintegration is proportional to the total number of nuclei present. If I want to remove the proportionality sign, I will introduce a constant. In this case, the constant is lambda. So I can write equation 1 as minus dn upon dt is equal to lambda into capital N. This is our equation 2. And here lambda is the constant of proportionality called the decay constant or disintegration constant. So I can write by rearrangement of the terms dn upon n is equal to minus lambda into dt. This is equation 3. And if I integrate the equation 3 on both the sides, I get integration dn upon n is equal to minus lambda integration dt. So we all know integration dn upon n, it comes out to be log of n. And this is equal to minus lambda into t plus c, where c is the constant of integration. And we have to find it by our initial conditions. What was our initial condition? Initially at time t is equal to 0, the total number of particles is equal to n0. So at t is equal to 0, n is equal to n0. So put this in equation 4 and I get log to the base e of n0. This is equal to c. So we have obtained the value of c. Put it in equation number 3. So log to the base e of n, this is equal to minus lambda into t plus log to the base e n0. So if I make rearrangement of the terms, I can get log to the base e of n0 upon n0. This is equal to minus lambda into t. Take antilog on both the sides. So n is equal to n0 e raised to the power minus lambda into t. This is our equation 5. And equation 5, if I am plotting it with n along y-axis and time t along the x-axis, I get a curve which is shown in this particular slide. So n is equal to n0 e raised to the power minus lambda into t. This is our equation number 5, is the law of radioactive decay. Now what can we interpret from this particular equation? It shows that the number of radioactive nuclei, it disintegrates or decays exponentially with the time. Simply, it means that as time passes by or time increases, the number of radioactive nuclei that remains, here n, capital N is the number of radioactive nuclei that remain at the time t. So this goes on decreasing. So if I plot the capital N along y-axis and time t along the x-axis, I get a curve which shows the decreasing nature of radioactive decay process. Means as the time increases, the number of nuclei goes on decreasing. So next we are going to see activity A. From equation 2 we can write minus dn upon dt is equal to lambda into capital N. Now here this quantity minus dn upon dt, this is called the activity of the radioactive sample and it is denoted by capital A. Activity is defined as the rate of radioactive disintegration or rate of decay of the sample minus dN upon dt. So it is rate of radioactive disintegration or rate of decay of the sample. That is called activity. The unit of activity is becquerel. It is named after a scientist, Henry Becquerel. It is denoted by small bq. And 1 becquerel is equal to 1 disintegration per second. Means if there is disintegration of 1 nuclei in 1 second, then that unit is called 1 becquerel. But the more general unit of radioactivity is Curie. You might have heard Madame Curie. It is named after her. Curie, and it is denoted by Ci, capital C, small I. And 1 Curie is equal to 3.7 into 10 raised to the power 10 becquerels. This means a unit of 1 Curie, it is derived from the activity of 1 gram of radium 226, that is radium 226. Curie is a larger unit of radioactivity, and as compared to becquerel, you might have observed this relation. 1 Curie is equal to 3.7 into 10 raised to the power 10 becquerel. So Curie is a larger unit of measurement of radioactivity and becquerel is a smaller unit. Now, how were these units given to these radioactivity phenomena? Now, for his discovery of spontaneous radioactivity in uranium salt, Becquerel was awarded half of the Nobel Prize for Physics in 1903, and the other half was given to Marie Curie and her husband Pierre Curie for their study of the Becquerel radiations, means the radiations that are emitted from the radioactive substances. Henry Becquerel is regarded as the father of radioactivity. So, as a honor to them for their discovery, the unit of radioactivity is given the name becquerel. It is a smaller unit and it represents 1 disintegration in 1 second. Higher unit is named after Marie Curie and it has value 3.7 into 10 raised to the power 10 becquerels. Means there should be 3.7 10 raised to the power 10 disintegration in 1 second. Then it will be called 1 Curie. So that's all about our topic of radioactivity. This was a general introduction about the law of radioactive decay and the units of radioactivity. So we stop. Have a nice